All right, welcome back everyone after the coffee break. So we'll finish with our last talk for the day by James Parkinson, who's joining us in person from the University of Sydney today. And James is speaking about automorphisms and opposition in spherical buildings. Thanks for coming, James.
Yeah, and thank you very much for having me. It's my first in-person talk. I've been teaching for quite a while. It's good to get myself out of the house. Neaten up my beard a little bit, spent last night looking for shoes, and anyway, so out of the house again. It's good to see the world. Also, sorry for being a bit late this morning. That was also a nice experience, 5 hours sitting there in peace and quiet by myself. But the bad thing is they gave me time to add to my notes, and like your room, I probably have way too much notes here. But similar to your room, in fact, we have some overlap of co-authors. In fact, everything here is joined with Hendrik. And also two other co-authors, Buki and I believe, for some parts. And by coincidence, similarly to your room, it's about a sort of a longish project with Hendrik that is coming somewhat to a conclusion, I guess. But again, like your room, E8 ends up being where we're at the end. It's not the same, it's a different problem to with your room, but as we'll see, there's actually some connections. Anyway, so I'll talk for a while about spherical buildings, and before I kind of say exactly what we're looking at here, thanks very much to both the previous speakers, because that helps a lot with the Coxeter group stuff, and also some of the language of the buildings. I'll talk about the origin of the problem, which unlike your rooms, which was a very old problem, this one really just got from a paper in 2009, stimulated the work. We did some stuff in the rank 2 case in 2015, did something in 2019, and we've got a couple of papers too, which are very close to coming out now in this year, maybe next year at the worst. Okay, so I'll just sort of scroll through these slides. So spherical buildings are similar to your room. I'm not going to say much about it, I'm not going to really define anything, but it's the geometric counterpart to groups of B type. That's things like Chevrolet groups, two-stick groups, and so on. And that really is TITS's 1974 classification that really says that they are the geometric counterpart to groups of B type. But groups of B type, I mean fairly generally, not just finite groups of B type. There's lots of ways of thinking of delta. Delta can be a spherical building. That's a simplicial complex. That's maybe the most simple way of thinking of it, I think, or the most unifying way that all of them can be thought of that way. Also chamber systems, that's a very related concept. Almost touched the screen, I probably should do it. The chambers, just to get the language in play, a chamber of a simplicial complex is by definition just the maximal simplex, the biggest simplexes there are. And also as incidence geometries, which is getting closer to the way Jeroen was talking, that's with points and lines, and that's an extremely powerful way of thinking of it, because it's more tuned to each different type of building. You have to change what your incidence geometry is. So it's going to be a uniform way, and you have to get more precise sometimes to do some more precise things. But anyway, we won't get into huge enough. As I said, I'm just trying to give an overview for the first while. I'm just going to talk about buildings, and then I'll try to say, I should say just roughly. What we're trying to roughly do is so people already know the words. We've got an automorphism of the spherical building. I want to understand the geometry of all of the simplices of the building, which are mapped onto opposite simplices by the automorphism. So studying fixed element structures is a very well-established part of all kinds of maths, but in particular studying buildings, we're trying to look at some kind of the other side of the coin. And as we'll see, it's really related. But I'll motivate it more as I go, but that's just the rough rule. So buildings, spherical buildings have a type, which as we've already seen a few times now, is just a spherical, which means finite Coxeter group, AN, BN, CN, DN, F4, E6, E8, all those ones, and they all have a diagram, and there's some of the diagrams. Now the nodes of the diagrams are in bijection with the types of the vertices of the simplicial complex, so we're thinking of the building in this general way as a simplicial complex. It's got these chambers, which are the maximal simplices, and each chamber has a vertex of each of the types, where the types are 1, 2, 3, 4, just whatever you want to call the vertices here. But the buildings are huge, really big things. Just to say a little bit, there's a relative position of chambers and that's an element of this finite Coxeter group, but it's a finite Coxeter group, so that means the geometry of this building has bounded diameter, a spherical building, and that's what gives you the notion of opposition, which is very important in this finite case, and it doesn't hold more generally when you move to infinite buildings, although there is a notion of twin buildings, which actually was part of what motivated this project, which I might say at a certain time. But let me say it very quickly now. I mean, if you have an automorphism in a twin building, that's when you've got two buildings, and an automorphism might interchange the two halves. And so that has empty fixed element structure. So all you could really work with there, if you want to look at something like that, is the geometry of the things mapped onto opposites. So that was part of the motivation. But we haven't got there. We got stuck with the spherical case and realized that was, whatever it was, 8 years of work just in the spherical case. So we got stuck there. Anyway, for chambers, chambers are opposite. It just means that their relative position, so to speak, is the longest element of the constant group. Also, just a kind of non-degeneracy, so to speak, delta is called thick if every panel, so in a sequential complex, panels of codimension 1 simplex, that would be an edge in this picture, is contained in at least 3 chambers, and I've drawn the chambers as triangles. So Mikkel's talk was about Coxeter groups, which are buildings, but they're buildings where every panel is contained in precisely 2 chambers. So you don't have this kind of thickness here. So just read my Q as 2. If this building came from some underlying field, that field would have 3 elements. It doesn't really matter. We'll do some examples. So we've talked about projected planes, projected spaces a few times. So quickly run through that. So an AN building, these are by far the simplest ones, really simple in a way, which is good because AN, a lot of the study of buildings, in particular spherical buildings, comes down to residue things where you look at sub-buildings. And in like a diagram like E8, there's an awful lot of type A residues. So if you can understand everything in type A, that's actually a pretty good thing. Anyway, so what are the AN buildings where you have this division ring, could be a field as well, and simplices are just non-trivial proper subspaces of n plus 1 dimensional space over F. And the chambers are flags, maximal flags. So if you think in terms of projected geometry, these guys are points, lines, planes, and so on and so forth. If you think in terms of vector spaces, they're dimensions 1, 2, 3, and so on and so forth. The simplices are just simplices. Anyway, that's an AN building. That's really what it is. And for n bigger than 2, all of the AN buildings arise in the way, all of the thick AN buildings arise in that way. But here's a picture that's more like a geometric picture. This is the case when n is 2, so a projected plane, and I've also picked the smallest possible field with 2 elements, and that's the Farno plane. And so I've drawn the 2 pictures of whether you think of it as an incidence geometry, points and lines. So remember, in this incidence geometry way of thinking of, you don't care where the point is on the line, it's just about the line contains those 3 points. Every point has 3 lines, and every line has 3 points going through it. And then you can draw it another way by drawing the points as black dots and the lines as open dots, and joining them by an edge if the point is on the line. So that makes a simplicial complex where the chambers over here, the chambers with the edges. Over here, the chambers are incident point line pairs, so a point that sits on the line. And I've said something about opposition here as well. This point here, opposite means as far away as possible. And well, it turns out in this particular building, to be opposite a point, you would have to be a line. I mean, the maximum distance you can get from that point, I have to find exactly what distance it's meant to mean, but anyway, it's sort of clear from the picture, is a line, not a point. Okay, so points are opposite lines, and similarly lines, this n is opposite this one Q over here, and anyway, I've drawn the same thing over there. Okay, so as opposition just means as far away as possible. What I've written here is this chamber PM, so that it's an incident point line pair, that's opposite this point line pair, because the point is opposite the corresponding line, and the line is opposite the corresponding point. Then other example, really the only 2 examples I can sensibly give, a brief account of, are called Generalized End Goals. These are the rank 2 buildings. Actually, the one I just drew was also rank 2, but now I'll just extend that a little bit further. A2, so we're going to. Anyway, this is another point line incidence geometry. There's an N up there, and these have no ordinary k-gons, where k-gon means thing, like k line edges. For k less than n, but any two elements are contained in some n-gon somewhere. So this thing looks awfully like it should be some kind of pentagon by the way I've drawn it, but that's just taking into account some automorphism of 4 to 5 or whatever. It's actually a quadrangle, it's a 4-gon. Any two, pick a point and a line, you can find some quadrangle if you bend your mind appropriately that contains them, and there's no triangles in this picture. Anyway, that's actually the building. So buildings are related to groups. If you took the symplectic group, SP4 over a field with two elements, that it acts in a super nice way on that geometry. In this case, however, note that lines are opposite lines. I mean, the furthest, you've got to just use your imagination what maximum distance means, but it's kind of clear in the picture. Those two are at maximum distance, and this guy and that guy are at maximum distance. But of course, that's also opposite that. I mean, things can be opposite lots of things. But anyway, opposition is what I would say is type preserved in this case, because lines are opposite lines and points are opposite points, rather than the previous case, which was type sort of swapping. Okay. Okay, so still just without getting to what our problem is, as you probably already see, opposition is a big, well, as I hinted at, opposition is the main theme, I guess, the whole research project, so I have to say a bit about it. Opposition in a Coxeter, in the buildings, or in a Coxeter group, in fact, just the longest element of the Coxeter group, induces an automorphism of the Coxeter graph. We already saw this in the A2 case that swapped the two types, and that's true for AN as well. So in projected space, points are opposite the maximal spaces, and lines are opposite the ones next. And just to clarify, I'm not saying every point is opposite every thing up here, but if two things are opposite, then and one was a point, then the other one would have had to have been at that flavour. For most of the types, actually, opposition is the identity. For B and C, it's the identity. For D4, it's the identity. And for D even, D2n, it's also the identity. For D5, it swaps those two nodes, but for D odd in general, it also swaps those two nodes. E6, it's this diagram, automorphism. And in fact, everything else, so F4 and so on, it's the identity. So it's actually not the identity in exactly AN, D odd, and E6, and all the other ones, it's the identity. But it's always a bit of a complication to view. Okay, so here's the origin of the problem, and it really came from this paper of Van Maldeghem, and it said that every non-trivial automorphism of a thick spherical building maps something to an opposite. So compare that to like a thin building, which in a generalized n-gon case is actually just an n-gon. Of course, you can just rotate it, and that doesn't map anything very far away. But as soon as you've got the thickness of this building, any non-trivial automorphism has to map something as far away as possible. Their theory, they were actually interested in automorphisms of buildings which weren't spherical, and then what their main theorem was that any non-trivial automorphism has unbounded displacements, like chambers which are mapped far and far away. But as a corollary of their result, they added at the end of the paper a section on this where the same techniques that they were using shows this result. And really it was, the aim of our work was really sort of came out of that. Well, they asked, well, I'll get to it in a second. The aim is really just to understand, in a sort of broad sense, what the geometry of, which I'm calling op theta, the elements which are mapped onto opposites by automorphism theta. So at the beginning it was just a very open problem or idea to investigate. As I say, part of the investigation was really actually thinking much higher than I'm talking today and much higher than we've gotten in the project, but thinking of automorphisms of twin buildings and studying. But that's another story when it's not yet done. Just to say, Abramenko ground tells us something fundamental already. That if there is nothing, that this opposition geometry of theta is non-empty if the automorphism is non-empty. But not the identity. Okay. Actually, I said this earlier as well. In contrast, the study of the fixed geometry, so called that fixed theta, let's say, is something that's used a lot for the Galois descent in buildings and A lot of with buildings, once you get used to them, like, you have to see these F4 buildings sitting inside the E8 buildings. They're kind of fixed geometries of certain automorphisms of the E8 building. I mean, these fixed geometries are very, well, let's say, well studied, and probably everything is known in a way about them now. But actually, we're going to see, perhaps surprisingly, that op theta and fixed theta are really closely linked. Well, they're linked, maybe not really closely linked. Let's say. Just to add a bit more, I mean, the most common situation, if you just took an arbitrary spherical building into a random automorphism, almost certainly it's going to map chambers to opposites. So this opposite geometry is going to contain a chamber. And for the sort of theory we're looking at here, these are the less interesting examples. We're trying to look at the sort of extreme borderline cases, so to speak. And by definition, these are called domestic. These are automorphisms which don't map any chamber to an opposite. In other words, this opposite geometry doesn't contain a maximal simplex. The word domestic here is meant to mean that it, I mean, you have to map something to an opposite. Brown tells us that. But to say you don't map a chamber means you're staying as close to home as possible. You still have to map something to an opposite, but not a maximal simplex. So you're trying to stay close to home. It's meant to help us understand that. And so just to re-summarize, really the project is to understand these domestic automorphisms and see if there is, to begin with, any nice theory about them. So with Brown's paper, they didn't really have clear examples. Well, they did, but they'd asked Hendrik for those, in fact, so that's how I got into it as well, because Hendrik. There is a simple example of generalized quadrangles. So these are the four bonds. So all the black stuff here is fixed. So you fix a point, fix all lines through that point, and fix all points on those lines. That's half the diameter of this graph, of this incidence geometry. And then start moving things. So these red lines swap them around and certain points get taken on. I mean, you can't just say that you can do that because these meet up here. So you've got to check that this actually makes an automorphism, and a point always for all quadrangles, but at least for the ones that come from BN pairs, from Lie theory. This is called the central delineation. And if you're in terms of the Chevalier generators, this would be an X alpha of A, where alpha is the highest group. Alpha is a log group. So the Chevalier generators for log groups will act in this way on the building. Even for E8, it'll do something similar. But anyway, the point of it is that it doesn't matter. But the point of this is that no line is mapped to an opposite because, well, all of the lines are drawn here, basically. I mean, it doesn't get any bigger than this. Of course, there's lines named for its points and stuff, but I've drawn the full diameter. So if a line gets moved, it just gets moved to a line that contains a point with the original line, and that's not opposite. However, points get mapped to opposites. These red dots here, they're going to opposites. So this thing maps points to opposites, but no lines to opposites, so we might call that line domestic. The domestic, remember, means not mapped to an opposite. So we think so the lines are not mapped to an opposite. I'll go over quickly another example, symplectic polarities of a polar space, of a projective space. So we have to be in even dimensions here, so F is now a field as well, not a skew field. So it's a commutative skew field as well. So we've got an even dimensional space taken on to generate this symplectic form and define an automorphism by mapping a space U, because remember they're the simplices of the projective space. A vector space U is getting mapped to its, I'm not sure what the right word is, annihilator or something of that space. But then the point is, if P is a point, just a one-dimensional space, then P is in its annihilator because symplectic forms have, P hit with P is 0, X hit with X is 0 in symplectic form. So P is actually n. And that means it's not mapped to an opposite. So in a projective space, point is mapped to the space that it's mapped to, that's opposite exactly when the point's not in the space, in fact. So, and actually, if you think a bit more about this, so I've drawn it in A7, it only maps simplices of these spaces, or whatever you want to think of them, of types 2, 4, and 6 get mapped to opposite types, but the opposites, but the other things I haven't encircled don't get mapped to opposites. Okay. So a little bit of the point is this is domestic for a kind of a, warrant's the wrong word, but for a really clear reason. It's domestic because it maps no points whatsoever to opposite objects. And so you can't, so it's not certainly not mapping a chamber to an opposite. Anyway, but just to illustrate how rare these domestic automorphisms are, so these ones which don't map a chamber to an opposite, if n is bigger than or equal to 2, duality just means duality means that it's an automorphism of AN which maps points to plane to. It doesn't map points to points, it maps points. It does the diagrams flip on types. Anyway, so the only domestic dualities of A and 2, so an odd AN, where n is bigger than 3, if you just write AN odd, they're all of this form. And for A even, there aren't any whatsoever, there aren't any domestic dualities. So in fact, what I'm saying here is in type AN, we have an almost complete classification of what the domestic automorphisms are, or domestic dualities. I'll come back to this field being the finite field with 2 elements later. That turns out to be where some exceptional things happen. And just alluding to what I said earlier, knowing a lot about type A will help us a lot better about general types. All right, anyway, so now I'll sort of start with what we have done, I guess, and this part's a while ago, so really quick. This is 2015 work. We started with rank 2, generalized end goals. But just to note, this is the rank where you don't have a classification of buildings. Rank 3 and above, they're equivalent to groups, more or less, to league style groups, let's say. But in rank 2, they're not. So that makes it sort of both easier because it's a small rank, rank 2. Of course, it's not too hard, but it's also harder because there's not a there's no classification of the objects. Just to comment though, or observe that for a 2n-gon, like a quadrangle, opposition is type preserving, so points are opposite points, lines are opposite lines. And for odd-gons, which are like the projected plane example, opposition is type swapping. Points are opposite plane lines and lines are opposite points. So I just want to make a comment here just to illustrate some of that, because to get your head around it a bit. So delineation, which just means a type preserving automorphism of the projected plane. So now we're an automorphism of projected plane, and now we're insisting on mapping points to points and lines to lines. This can't map any point to an opposite, because things that are opposite to points are lines, and you're mapping points to points, so you're stuffed. And it also can't map any line to an opposite. But it seems to contradict Abramenko-Brown because something's meant to get mapped to an opposite. But it's okay. Opposition geometry is not empty. It only maps chambers to opposites, but not points or lines. It's a little bit confusing. So there's the projected plane, and there's the theta, just that reflection. That maps points to points and lines to lines. It maps this point to this point. But the point is this red chamber, incident point one pair, is mapped to this one because P is opposite L theta and L is opposite P theta. So the chamber is mapped to an opposite, but not the sub-simplices of the chamber. That's a bit annoying in the mind, I think, to deal with. So just to simplify, I'm going to talk about something called automorphism, which is not a real word, but an automorphism is going to mean an automorphism whose action on the type set of the building agrees with the action of opposition. So this is not an automorphism, but it's opposition in a projected plane swaps the types. This automorphism preserves types. So I'm just not going to talk about that one anymore. We can deal with all of that, of course, but why is this nice? Because this means if something is mapped to an opposite, some simplex, then all sub-simplices will also be mapped to opposites. That's the property that automorphisms enjoy that non-automorphisms don't enjoy. Sorry for some silly words. Okay, anyway, so let's just say that all automorphisms for the talk are going to preserve type. So with that convention, if we're looking at automorphisms, just to repeat something I sort of said earlier a little bit, not quite. But so if you have an automorphism of a generalized end goal, well, it can be domestic for 3 possible reasons. The first is that there's no point mapped to an opposite point on line, whatever respectively it is. The second, so then you certainly domestic. The second one is you map a line to an opposite. And the third one is that you, somewhere in the building, you do map some point to an opposite, and you do map some line to an opposite, but they're never in an incident point line pair, so you don't map a chamber to an opposite. Okay, so that third case is kind of the weird one. Points to opposites, lines to opposites, but they're never incident point line pair. Anyway, here's an example. Okay, I can do this example. Okay, so I'm going to, for the projected plane, it needs to be an automorphism. It needs to map points to lines. And anyway, I'll write it out. So map that point to that line, this line to that point, this point to that line, this line to that point, this point to that line, this line to that point, this point back to this line, this one to here. So far I've got an 8 cycle. I haven't defined the whole thing yet, but it's got order at least 8 already. And then for the remaining ones, this one's going to get mapped to this line. This line in turn gets mapped to this point in the middle here. This point goes across to this line, and then back again. So this is the 4 cycle. And then finally I have to say what these guys do. That point goes to that line, and that line back to that point. So while it's not that clear looking straight at that picture, but this has the property that, well, it is clear that maps points to opposites. This point here gets mapped to this line here, which is opposite. So that's okay. And also similarly, this line here gets mapped to this point, and they're opposite one another. Yet, staring out a little bit longer, there's no incident point line pair. So for all of the points that are mapped to opposites, the corresponding lines through them aren't mapped to opposites. Similarly, for all lines mapped to opposites, the corresponding points on them are not mapped to opposites. So this is an example of this third type, exceptional domestic. There are points mapped to opposites, there are lines mapped to opposites, but no incident point line pair. Anyway, this rank 2 case does help us understand the higher rank case. Through it. So a theorem from back a while ago. So let's think through it. So let's talk about the automorphisms again. So for an odd gon, like a projected plane or a 5-gon, 7-gon, and so on, no automorphism can be either point domestic or line domestic. So basically it means for the 2 basic reasons of being domestic, that can't happen in that for odd gons. For even gons, you can be point or line domestic. But if you are, I'm not going to define what this is, avoiding subspace or a dual. So if you're point domestic or line domestic, i.e. you map no points to opposites or no lines to opposites, then the fixed element structure is some very, very highly structured and very large subgeometry of the building, of the polygon, which is a special type of building. I can quickly say what it is. So it's either a regular ovoid, which Jeroen talked about, or it's a ball of radius half the diameter of the, so radius n in this case, in the incidence graph. That was like that example of the generalized quadrangle that we fixed half of it and then started moving things. Or it's a what's called a large full subpolygon. So it's a really beautiful structure inside there. Or the dual of all those objects, which are spreads or all centered at lines or large ideal subpolygons. But the point is, they're things that they're basically the only types of subgeometries you study in those things. Well, the most important types of subgeometries that occur for those things. And then finally, because I want to extract some morals from this story in a minute, that's why I'm emphasizing certain things. Finally, for the exceptional ones, these exceptional domestic automorphisms, the ones that have points to opposites and lines to opposites, but no chamber to opposite, there's super few of those. They only occur for the Fano plane, which is that's exactly the example I just drew with the 8 cycle and stuff. And indeed, in that thing is unique up to conjugation. So there's that one that I drew. For generalized quadrangles of smallest orders, which are ordered 2, 2, so that means 3 points on each line and 3 lines through each point. For example, this one means 4 lines through each point and 6. You add 1 plane anyway, or the dual of all of these. But anyway, the point is, these are the smallest generalized quadrangles you can have. This is the one I drew earlier, in fact. And also the smallest generalized hexagons of order 2, 2, and 2, 8. They're the smallest ones, gives us. So there are very, very few of those. And just say quickly, techniques, there's a whole lot of counting stuff, and counting techniques and also spectral techniques, because there's no classification for these objects. So we really had to, so algebraic graph theory stuff, like finding some algebra of some adjacency operators on the object, and then finding its decomposing some representation and finding multiplicities that were some fractions, and then with square roots and stuff, and all of those things had to actually be integers because they're multiplicities, and that somehow, so it took ages actually, it was a headache. The moral though, what I think we have to take out of that is that typically if theta is domestic, so typically if theta doesn't map any chamber to an opposite, then it does that for some rather clear reason. So the general case is that it's domestic on some type. What I was talking about was either point domestic or line domestic, not this weird exceptional domestic one. Second moral is that to be domestic typically means you have a highly structured and very large fixed geometry. And that makes complete sense, in fact, because domestic means, remember, something of that, so some vertex of a certain type is not mapped to an opposite, let's say. But if your fixed geometry was super large, then any vertex of that type is going to be relatively close to something in your fixed geometry. Well, that's fixed, so you can't be moving that point very far away to the top. So the moral is kind of clear that it should be linked with large fixed subgeometries. However, just to emphasize that that's not the full case, in this 3-5 case here, the fixed geometry of this automorphism is empty. It doesn't fix anything, in fact, but it still manages to be domestic. But anyway, there are finitely many small counter examples to the general moral. So that's the second moral, so to speak, is that the exceptions are in the super tiny buildings where there's some 2 or 3 somewhere in the thicknesses. Any questions? Very quick.
Yeah, you mentioned spectral techniques. What does that mean?
Yeah, so spectral, I meant eigenvalues. So a good example, so the way you prove, so the only proof known so far of the Phi-Hickman theorem, which says that finite generalized end goals only exist for m equals 2, 3, 4, 6, and 8, proceeds as follows. So you look at the adjacency, so think of they're called incidence matrices. So you look at think of the thing as a graph, like I drew back here. Might be easier. The right-hand side here. And define so there's a distance on points here, like just a graph distance. And define a matrix A subscript k, for each k being up to 3, because the maximum distance is 3 here, to be a matrix with zeros in. So it's rows and columns are indexed by the vertices, and it's got a 1 exactly if the distance between x and y is k. 0 is everywhere else. So in particular, A1 is the adjacency that are passing in order, basically, something of the graph. And these graphs have the special property that linear span of those matrices actually is an algebra, so multiplying 2 of those matrices together is again written in terms of linear combination of those matrices. So that's called a distance regular graph. And so what you've really got there is however many vertices there are, 21, whatever it is, you've got a 21-dimensional representation of this particular algebra. So think of that algebra now, we haven't explicitly represented, but now treated as an abstract algebra in your mind. But you're given now a geometric representation with 21 by 21-dimensional one. And now you decompose that, so it also happens to be a commutative algebra in this case, but anyway, that doesn't matter, so just think it's an algebra. And so you decompose that 21-dimensional thing into irreducible representations. But you do it in a way that uses some clever linear algebra with some inner products and stuff. I mean, you do it like representation theory of finite groups, where you've got characters and inner products of characters. Yeah, so you're not decomposing it by hand, you're decomposing it in a kind of abstract way where you get formulas for the multiplicity in terms of certain inner products and stuff. And then you compute those formulas, and just by magic, well, not by magic, I mean, they just turn out to be rational functions in the parameters, the thicknesses of the building, and the m, and they have to be square roots and stuff too, because that comes into it. But they have to be integers because they're multiplicities. And that puts serious constraints on the possible m, the m-gon, what its diameter is, and moreover on particular parameters, how many lines are incident points and how many points lie on each line. And just looking at that, that is the proof of the Phi-Hickman theorem. It's bizarre, like you don't get it from a geometric way, you get it from looking at some algebra and decomposing it into irreducibles. And that's what we did here. Roughly speaking, we've got the algebra from the underlying building, that's what I just talked about. But then you throw in a matrix with the automorphism as well, so you kind of extend your algebra a little bit. You just make the permutation representation of the automorphism and decompose that algebra, roughly speaking. So I guess I'd call it algebraic graph theory or something like that, but it worked, which was, but for, yeah, anyway, I won't get carried away. Good, so we're almost done. We're almost in the general case anyway. So that was the moral. Moral, it's domestic because it's domestic on some vertex type, highly structured fixed geometry. The exceptions are very rare and small. So our next kind of part of our project, I guess, was so we want to move to higher rank, of course. And at first it seemed like a mess. Like, what are the possible, just saying an automorphism of an E8 building doesn't map a J to an opposite. What can you say about that? So the idea of these opposition diagrams was to try to give some structure to just a framework with which to work, and so I've got to explain it, and it worked well, it turned out. So we're now got an arbitrary building. Let's stick with automorphisms just because it's easier to think about. And now I'm going to define the diagram of theta B, take the Coxeter diagram of the associated Coxeter group, and just encircle those nodes for which there's a vertex of that type mapped to an opposite by theta. So underline there's a theta here that we're not seeing, of course, but I'm just encircling the types. So this would be an E8 building where vertices of types 1 and 8, and only those of type 1 and 8, are mapped onto opposite vertices. Just emphasize not all type 1 vertices are mapped onto opposites, but there is a type 1 vertex mapped onto an opposite. So we'll call that the opposition diagram. That's what I just said. Okay, yeah, so the next definition seems to be strange unless I explain it here. So in this example, I'm saying that there are type 1 and type 8 vertices mapped onto opposites. But I'm not saying that somewhere there's a type 1,8 simplex mapped to an opposite. That would mean that there's a chamber whose type 1 and type 8 vertex are both mapped onto opposites. So they could be a long way away from each other, these guys that are opposites. The next definition is as we were investigating, this seemed to be a good definition, so I'm going to call theta cat if whenever there's simplices of types J1 and J2 mapped onto opposites, there's a simplex of the union mapped to opposites. In other words, if I let J be the union of all the encircled nodes, so all of the types for which there's a vertex of that type mapped to an opposite, take J to be that union, then there's actually a simplex of that type somewhere in the building mapped to an opposite. It's definitely not saying that every type 1 vertex is contained in such a simplex, but somewhere there's a type 1,8 simplex mapped to an opposite. Okay. So it's some closure property in the partially ordered set of all simplex types that are mapped to opposite. Cat, that's what it means. It means that has a unique maximal element in that partially ordered set. It's a cat when you draw it like that. I don't know, you have to think of words. Anyway, that's what I just said. So exceptional domestic automorphisms are not cat. Because the opposition diagram for these m-gons, they map by points and lines to opposite, but no incident point line pair. So no change. That's not cat. Okay? If that was a capped automorphism, then that's exactly the same as saying it's not domestic. It maps some chamber to an opposite. Okay. So knowing that an automorphism is capped turns out to be super powerful, and a bit surprisingly. And the point is it facilitates inductive arguments, which is, I guess, somehow analogous to what Jeroen was talking about. Where we're looking at residues and so on. And let me just explain that very briefly. So let's say we're a capped automorphism, and take a simplex of this maximal type that I called J earlier, mapped onto an opposite. So in our E8 example, that's a type 1,8 simplex, so contained in some chamber, mapped onto an opposite. And then take any sub-simplex of that simplex, So for example, in that E8 case, I might take the type 1 vertex with my 1,8 simplex that was mapped to opposites. And now that has a thing called the residue, which is just roughly put everything that's, well, not roughly put, it's everything that's incident with that, that's contained in some chamber with that type 1 vertex. So that's all that junk there. But the building's huge. I mean, an E8 building has diameter 70 billion trillion or whatever it is. It's enormous. So there's a lot of distance between here and here. But the point is, this guy's mapped onto an opposite. That's what I've drawn there, because it's a type G simplex mapped onto an opposite. It's a subsimplex of such a thing. And we're talking about automorphism. So what you do is you map theta maps this residue across to this residue, and then in general building language, you can always project back onto a residue. So you do that. That takes, to each thing over here, there's a unique closest thing over here. So you map across and then come back. So that defines an automorphism of just this residue. And residues of buildings are, again, buildings. And they're, in fact, the building obtained by, if this was type 1 in our E8, just put your hand over the type 1 vertex, and whatever you get left, which would be a D7, that's what the type of that residue is. It's a building of type D7. And the key point with this capness is that the opposition diagram, that projection, map across, project back, is the subdiagram of our original opposition diagram obtained by just removing the nodes in sigma prime. What that really means, if you think about it, means if something in here is mapped to an opposite over here, then when you project it back, it's mapped to an opposite in that residue. So it's a different notion of opposite in that new little building there. So something that was mapped to here to an opposite and then mapped back, it would be opposite where it started in that residue. That's what this is saying. And so it means that you can just start with a big complicated E8 diagram, start putting your hands on the nodes, and if you eventually get some disallowed opposition diagram, then that original opposition diagram was not allowed. It was not allowed for a capped automorphism anyway. So that's the point. So now we've got a big diagram, keep putting your hand on it until eventually you get some stupid thing like a projected plane where you're mapping only points to opposites but no lines to opposites, and that's something that's impossible. That kind of thing. So, as I say, combined with our understanding of residues of type AN, that proves to be very useful. And here's an example. So here's an E7 diagram. This is not a valid opposition diagram for a capped automorphism, because if I put my hand there, well, don't worry about the isolated node because it's all about connected components. So looking at that, that's an A5, and that's not a valid A5 opposition diagram. Well, what I said earlier, we classified all the domestic things in AN, and that's not one of them. But of course, like maybe capped, maybe nothing's capped. And so we made this definition about capped, saying that you've got this simplex of the maximal type mapped to an opposite. But that was the main theorem of that work. Is that in fact every automorphism of a large spherical building, rank at least 3, is capped. And large means no Fano plane residues. So that's the ones where you've got the super small buildings where you've got a 2 over the field of order 2, or some twisted group where you've got 2s and 4s and stuff like that. But anyway, in all cases, they're the very smallest of the buildings in terms of the smallest possible field you can put in. It turns out in those exceptions, just like in the projected plane that I drew, the exceptional domestic thing, they do also exist in fields with 2 elements. So that's why this was hard to prove, I think, because it's not true that all automorphisms are capped, only if the field is sufficiently large. That's what made it hard. Anyway, I won't really say how we proved it. Except for saying, maybe I'll just say we had to look very carefully at polar spaces, which are types B, C, and D. And then also we had to have a very in-depth understanding of the geometry of an F4 building and E7 buildings. So that turned out to be enough. Understanding certain configurations in F4, E7, and all polar spaces. We just had to deal with them. But anyway. The corollary is that the opposition diagrams are super restricted. So for example, in E8, I'm going to do an example of E7, but E8, let's do E7. So for E7, a priori, how many opposition diagrams should there be? Well, you should be able to pick whether you encircle that node independently. I would say be 2 to the 7, which is some relatively large number. But in fact, with that theorem in hand, these are the only opposition diagrams that you get for E7. You just get these 6. And in fact, the first one, because nothing's encircled by Abravanco-Brown, that means theta is the identity. So that's not so interesting. This one, because we're capped, we're assuming we're in a field's not the field of order 2. Okay, so once we know we're capped, this is not domestic. So while I'm not saying that's not an interesting automorphism, there's an awful lot of automorphisms with that diagram. Of course, they're interesting, but not for the sort of thing we're looking at. And then there's the other ones. There just happens to be one with one node encircled, 2, 3, and 4. So they have convenient names, E7, 1, up to 4. And that turns out to be the only ones. We were really happy when that came out that way, because that opens up the possibility now and puts a bit of a framework around saying, well, there's only 4 diagrams really to look at, so it's conceivable that you could classify for each of those 4 diagrams the automorphisms that have that as its opposition diagram. Before you've got the structure of the opposition diagrams, you're a little bit lost in the woods as to what to do. But notice this guy and this guy appeared in Jeroen's talk. That was on his 3rd row, 4th column, and his 4th row, 3rd column. There's some mysteries there of where. Anyway, they're all tits indices. That's related to what Jeroen said as well. So for algebraic groups, that's actually not a complete coincidence, as we'll see soon. But we don't know what a tits index is. Automorphisms of small buildings, the ones with finite planes, these really do counter the. It turns out the opposition diagrams happen to actually be the same, but you have to think of them more carefully, because there are things with this opposition diagram which are not domestic. It's very, because it maps vertices of every single type here to an opposite, it somehow manages to map no chamber to an opposite. Well, we can prove various things about that. No, I won't talk about that. But we did write a paper about the small buildings too. Anyway, and it's nice what you can say there. Anyway, that's what I just said. The understanding of these diagrams puts the right framework around trying to classify automorphisms for each of the non-trivial, the empty diagram's trivial, the full diagram's trivial, and trivial, whatever you want to say. So now the final section, and where we are now, is we've made some progress on that program, and we see the same model that we saw in the generalized polygon case. We've actually essentially done it with the classical types. I won't say more about that, because somehow the exceptional types are a bit more exceptional. So the classical types, that paper will be out fairly soon. It's just sitting on my desk requiring some beautification or something. And we're sort of almost done with the exceptional cases too, except a bit like Jeroen, maybe for different reasons, I'm not sure. E8 is still a bit of a mystery. And also the sort of really exotic mixed F4 buildings. We can probably do it, I guess. And here's a flavour of the result. So this is where I'll finish after this result, these 2 results. So first there's a dichotomy of whether it, we didn't really see it or need to make that distinction earlier, but there's a dichotomy. So you've got this domestic automorphism, capped, so not mapping each other to opposite and stuff. And it'll matter now, there'll be quite different flavours if they fix a chamber of the building, so if the fixed geometry contains a chamber, or if they fix no chamber. So it turns out to be quite different behaviour. So here's one theorem. This is the chamber fixing case. So here I'm saying we've got an automorphism of E7, an E7 building over a field F. Again, F's not the field with 2 elements because there's some annoying things happen. And we've got a domestic automorphism theta, and we're going to assume it fixes a chamber. And actually, you can really say very precisely what it is. It's either a product of K perpendicular root relations. So what that means is, if you're familiar with Chevrolet generator stuff like the X alpha of A's, and you build the Chevrolet group, the alphas are the roots, and so I mean you're a product of 4 of those X alpha A's, with the alphas being perpendicular in the root system of type E7. So X beta 1A, X beta 2, A B, X beta 3, with the beta 1, beta 2, beta 3 all perpendicular. And it also just is beautiful that the K, you're a product of K of these perpendicular root relations, and that gives you how many nodes are in circle. And there's a second case, homologies. These are things which fix an apartment of the building. There's some homologies with very, very precise forms. You can really pin them down. We think that this diagram or this diagram. So the proof of this is purely, it's not really geometric, it's purely in the Chevrolet group. Lots of commutator relations and some really nice, in my view, I like that bit. But I also really like the next bit. The next bit is the case where we don't fix a chamber. I should say that last theorem, it's not quite fit. That theorem should have inverted commas, I think. This one I'm 100% sure of. In this case, it's just when k is 4. I'm saying if and only if here, definitely the product of k perpendicular relations does have that diagram, but of course you want to show everything with that diagram is of that form and very, very close to getting there. I can write them all out in Chevrolet generators, but I have to check that they're conjugated into the right thing. Anyway, not fixing a chamber is a very different flavour there. It depends much more on the field. So if the field, this is also even known, but anyway, if the field emits a quadratic extension, so I'm saying we're starting with the domestic automorphism, then either F emits a quadratic extension and your opposition diagram is this one, and I can also now say dually what your fixed structure is, it's this one, which if you think of these as the vertices of types 1, 2, 3, 4 of an F4 building, this is an F4 building. Over this, it'll be mixed between the field and the quadratic extension as the sort of thicknesses. Type B. So there's already this duality of the TITS indices, which is sort of, these are TITS indices, the fixed structures, so that's kind of where they come from, and there's opposition diagrams, and there's some kind of translation between them, and that's emphasized by this next theorem. So, next part, maybe there's a quaternion extension of your field, so there's a quaternion there with quaternion ring over your base field. And then your opposition diagram is of this form, which is the other one, and your fixed diagram is the other one. So this is in the magic square. I don't really understand why, but these are these two, the 3-4 column and the 4-3 column. 4-3 entry. There's sort of some duality. And then there is actually another type as well. There's another example with opposition diagram is set 4 over quadratic extensions. This one doesn't have a fixed diagram. Well, it sort of does. It fixes vertices of every single type, but it doesn't fix a chamber. So it's fixed diagrams. Again, with these TITS indices, these fix things of each of these three types, but actually fixes a simplex of that type. I think that's all I want to say. Yeah, so thank you very much. That's it.
Thank you very much for that, James. Do we have any questions or comments?
I have a question. So you only get these exceptions in what turn out to be known generalized polygons. Were you led there all the way by combinatorial reasoning, or did you at some point use geometric characterizations of these classical examples?
We were led, so let's say we were going to study hexagons. So we're looking at hexagons and we've got the parameters S and T. So we were first led by pure combinatorics and this spectral theory and so on, spectral techniques, down to saying that the S and the T have to be either 2, 2, 2 and 2, 8, whatever it was. But then to actually see that there exists one, we use the fact that there's a unique generalized hexagon of each of those orders. And then we went to the atlas or whatever, and then we checked that there really is an automorphism that does what we wanted, and that all of the other conjugacy classes don't do that thing. So we used to do both.
Yeah, but that's a bit lucky in some sense, because if you would come to an unknown parameter, you would be completely stuck, I guess.
Well, I was going to say that the hardest part actually was octagons, and the smallest octagon is the 2-4 octagon. Which sadly is not known to be unique yet. It's not known to be the Reed-Tits one, to be definitely that. So if there did exist one for the Reed-Tits octagon, it would have been super annoying. So we would have gotten down to saying the parameters have to be 2-4, and then we could look at the Reed-Tits one, but to somehow eliminate it from some other octagon which may or may not exist with those same parameters. So in fact, a lot of the time was spent on the octagon case proving that no examples exist in 3-6 and all this kind of stupid stuff where there's like 3 line or whatever it has to be, where there's almost certainly not even an octagon with those parameters. But no one knows that, so we have to spend like 30 pages ruling out, proving things that don't exist in objects that probably don't exist.
Okay. So you can't use any of the sort of characterizations of the 2-4 octagon under extra assumptions, because there are a couple of those, I think.
It's possible that maybe we could have said that if an automorphism exists like this, then the polygon has to have some properties, and then it's possible maybe. But we're happy at that point just to say those polygons are known to be unique, and we'll just look carefully at those. We did, in the theorem I did also say it was true for finite, so that about the classification of exceptional domestic things, it was true for finite polygons and Mufang ones. I also slightly lied there. The Mufang octagons, we haven't actually finished that to check that there aren't any. So Mufang, now I'm saying like I want an infinite octagon, but I'm not going to take a free construction one, I'm going to take one that comes from a Lie group. And almost certainly they don't exist there either, but we do have to write that out carefully. But for hexagons, we could prove for all the families of Mufang hexagons, these automorphisms don't exist, even if there was an infinite one. And then we could use geometric characterizations of the Mufang hexagons. Rather than all 6 families or whatever, we would have to do all of this.
Thanks, James.
Yeah, pleasure. Thanks, you.
Any other questions or comments?
Yeah, you just said that you spend a lot of time proving that certain structures don't exist in objects that might not exist. Might that give you some insight into whether the objects exist?
Maybe, but then thinking back on like the analogy or what we sort of built on from how those spectral kind of techniques were working, it was really doing the Veit-Higman theorem with a small twist with the automorphism. And the Veit-Higman theorem has already been, well, that technique is unable to show that these octagons don't exist. So I can't remember what the things are, but there's something like for an octagon with parameters s and t, so that means s plus 1 lines per point and s t plus 1 points per line. Some equation has to hold, like st squared plus st plus 1 divided by s plus t has to be an integer, square root of 2st has to be an integer and stuff like that, which shows you that s can't equal t already. But yeah, so for the case of 3, 6, it's probably not 6, it's probably 3, 12 or something, which satisfies those all of the known constraints. I suspect just throwing in the automorphism might not. Or can you tell us anything? I mean, it's possible, but I think people have tried really hard with those spectral techniques. Not to say there's not more to be done, of course, but people have pushed those techniques really hard. Partly motivated by the lack of geometric insight into those. It's funny, like as the girth of the polygons get larger, so as the M of the M-gon gets larger, you just start losing geometry. Like the 3-gons, they're projected planes, and they're like the easiest. That's the first example of a point plane geometry, basically. So they're the easiest things to study. Not that they're classified or anything, but it's the easiest thing to to understand. And then quadrangles are pretty good geometry. Already hexagons are getting pretty hard, and then octagons, the girth, the diameter is just too big for geometric reasoning. And that's where it's this nice coincidence that the spectral graph theory stuff says nothing for the small girth, basically. It doesn't tell you anything about generalized, about projected planes, but it tells you an awful lot about octagons. Where geometry tells you heaps over here and not over here. And it's the same thing with this theorem, actually. It's the same flavour that for this chamber fixing case anyway, it's pure algebra, and geometry you just lose the geometry. Once you're fixing a chamber, you haven't got control over the geometry properly. Or at least the fixed geometry is not going to be some nice object. And then here, there's no way I can approach these non-chamber fixing ones using Chevrolet group techniques. I'd just be lost. But here, you start using geometry. I like this area, and I like working with Hendrik for that reason. It is very, very geometric, and I'm more algebraic, I guess. And it works well.
Okay, anything else? Any other questions or comments? I have one very basic question, James, not working in this area. So the whole concept of opposition only makes sense when the Coxeter group is finite, right? Whereas fixed points are something you can study in buildings of any type. So is there hope to match this up for general buildings somehow?
Yeah, so it's what I tried to allude to actually, so with the twin buildings, so what's the point of twin? So of course, to understand twin buildings, you want to first understand buildings fairly well. But what's the moral of twin buildings? It's the opposition is so useful for finite spherical buildings, and in fact, just spherical Coxeter groups. Opposition is used all the time. The opposition relation. It's indispensable for a lot of the theorems and properties to hold. So the idea with twin building was just to say, well, if you're looking at like a Kac-Moody group or something, you've got B, the subgroup B, like the Borel, but it's also a negative Borel. In the finite, when the Coxeter group is finite, there's an element of the Coxeter group which conjugates this to this one. So it's like, roughly speaking, upper triangular matrices get conjugated to lower triangular. And that's the opposition relation in spherical. But in a Kac-Moody group of non-spherical type, there's no element. You'd have to map infinitely many roots to positive roots to negative roots to conjugate this to this, and no element of the Val group does that. So you just don't have this property. But the idea of Titz and others, and also Ronan was big in the area, is to look at a twin building, which is now you take the G mod B and the G mod B negative, the negative Borel. So you've got, these give you two buildings just sitting there independently there. Well, if you get them from a Kac-Moody group, they're two isomorphic buildings sitting here. But the Kac-Moody relation is the Birkhoff relation decomposition, which decomposes elements of G of the group into B minus W, B plus double cosets. And what this gives you, it gives you a way of measuring a distance from this building to this building. And that's the opposition relation now for the twin building. And it's actually, because you don't really have a longest element, it's set up such that if that distance is the identity in the underlying Coxeter group, that's what opposite means. So you've got to like just flip it around a little bit. But anyway, so in the Kac-Moody theory, there's a lot of cases where you look at automorphisms which swap the two buildings, like that swaps the positive Borel with the negative Borel. And exactly as you say, there's no fixed elements for that now. So these geometric techniques, the fixed element structures just don't make sense. But our sort of part of our motivation of getting into it was, well, as this opposite geometry. You can look at studying this as a de facto kind of replacement. But the point was, as soon as you tried to do that, just for an affine twin building, you start straight away you have to understand what happens on residues. And the residues are finite buildings. So straight away it's like, oh, I have to understand how this opposition works on spherical buildings. And that's what took us these 8 years or whatever to do. And so there's hope that we can extend it to like affine Kac-Moody groups or something, and say something useful then about farm theory, I think it's called, where they look at involutions that do these things, and it gives you, if certain special things happen, then you get nice presentations for the group that you started with. That's kind of the model. So yeah, I think there is something there. But yeah, I think for like A2 tilde, twin A2 tilde buildings, I can understand this opposition geometry. But as soon as it's A3 tilde, actually I'm already, even everything we know about the finite case, what might I want to prove? We'd want to prove that they're capped. I mean, if the field's big enough that it has this cap property, that's already not obvious. So, anyway, yeah, it's a good question. I think there's a lot more going on.
Okay. Any final comments, questions, remarks? If not, let's thank all three speakers of the day one more time.